what we're going to start off with is the expansion of the binomial x plus y to the power of n. So if we start off with x plus y to the power of 0, what do we know happens when we put something to the power of 0? What do we get?
1.
1. Anything to the power of 0 will always equal 1. What would x plus y to the power of 0 equal? What does x plus y to the power of 1 mean? Means I multiply by itself one time. So I would get x plus y. If I have x plus y squared, that means it's x plus y times x plus y. What would that equal?
X squared minus 2xy plus y squared.
Yep. Okay. Now x plus y cubed, I can take this x squared plus 2xy plus y squared and multiply it by x plus y. So I'm going to give you a moment to do that, and then you can tell me what you get. So what did you get?
X cubed plus 3x squared y plus 3xy squared plus 1.
So if you're trying to figure out which order we should write these in, because the x comes first, let's start in descending order from x's. So I have x cubed, x squared, x, and then y cubed. So if I take a look at y to the power of 4, it's going to be taking this and multiplying it by x plus y. So I want you to do that one on your own as well. Okay, so what do I get when I take x plus y and I bring it to the power of 4? So I know that I'm going to have an x to the power of 4. What do I have next?
4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4.
Okay, so in part C, we're going to just write these out again so that we can kind of see them a little bit more neatly. So I get x plus y to the power of 0 is 1, x plus y to the power of 1, 2xy plus y squared, 3x squared y plus 3xy squared plus y cubed, 4x to the power of 3y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. So all I've done is I've just recopied the answers that we did above in that space. When I take x plus y squared and I expand it out, so x plus y squared, how many terms did I get? 3 terms. When I take x plus y cubed and I expand it out, how many terms did I get? 4. And when I took x plus y to the power of 4 and I expanded it out, how many terms did I get? 5. So if I do x plus y to the power of 20, how many terms could I expect to get? 21. Okay. Now let's look at the exponents, the sum of the exponents in each expansion. So if I look at the first one, x plus y squared, I I have an exponent of 2 here. This should be a 2 up here. An exponent of 2 on my y. And then what are the exponents on the x and y here? The exponents are each 1. And the sum of 1 and 1 is 2. So the sum of the exponents in each term is 2. If I look at my y cubed, or sorry, my x plus y cubed, I have an exponent of 3 here, an exponent of 3 here, and what is the sum of the exponents in the 2 middle terms? 3. If I take a look at x plus y to the power of 4, what are the sum of the exponents in each term? 4. I have 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4. So if I had x plus y to the power of 20, what would the sum of the exponents be in every single term? 20. So if I had a term that was an x cubed, what would the y have to be in order for it to belong to this expansion? 17. Because that would give me my 20. That follows so far with the pattern? Okay. So now what we're going to look at is, we call it an array, but what we're going to look at is we're going to look at the coefficients. So if I look at the array x plus y to the power of 0, I only get 1. X plus y to the power of 1, I get x plus y. But what are the coefficients on the x and the y? So what are the numbers in front of the x and the y? 1 for each of them. In my x plus y squared, I get this 1, this 2, and this 1. So what do I get with x plus y cubed? 1, 3, 3, 1. And x plus y to the power of 4. 1, 4, 6, 4. Okay? And what I'm going to do with this array is I'm going to slightly shift the numbers to form a triangle. So I put the first one in the middle, and then the 1 and the 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Now, suppose we wanted to do the next row in the triangle. I wanted to continue it down. What do you think I would start with? Follow the pattern. What do you think the next number would be?
5.
5. What do you think I would end up with on this end? Probably a 1. And what do you think would come before it? 5. Okay. How many terms should I expect to have in this row? 6. So I need 2 more. Any idea of what these 2 numbers would be in looking at the patterns?
10 and 10.
How'd you get the 10 and the 10?
I did 4 plus 6 for each one.
So 4 plus 6 gives me the 10. Because right here, 3 and 3 gave me the 6. 1 and 2 gave me the 3. Good. Okay, so the next page just looks at some of the properties of doing an expansion of x plus y to the power of n. So they've expanded out up to the power of 5. And what we want to do is we want to extend beyond the first 5. So I have 1 term, 2 terms, 3 terms, 4 terms, 5, 6. So in my x plus y to the power of n, how many terms could I expect to have? So when I have a power of 4, how many terms do I have? 5 terms. If I have a power of 5, how many terms do I have?
6.
So I always have one more. So if I have n terms, or sorry, if I have n to the power, how many terms would I have?
N plus 1.
N plus 1. Okay. If I look at each individual term and I look at the exponents, what are the sum of the exponents in each term? So in my x plus y to the power of 4, what was the sum of the exponents in each term? 4. So if I have x plus y to the power of n, what would the sum of the terms be in each term? N. Good. The exponents of x, look at the exponents, tell me what they do as I go from left to right.
Decrease.
They decrease. And they decrease from n, so from 5 to 0. Because this one right here would be x to the power of 0, which I don't need to write in. What do my powers of y do as I go from left to right? They increase. And then finally we have the coefficients. So the coefficients, if I go back to the bottom of the previous page, if I look at these coefficients, what can you tell me about the arrangement that they make in the rows? So I have 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. If I cut a line down the middle, what do I notice about this half to this half? It's like reflected. 1, 3, 3, 1. If I ignore those middle terms, 1, 4, 4, 1. 1, 5, 10, 10, 5, 1. So I get a symmetrical arrangement. Which means if I gave you part of the arrangements, and I said that I had 1, 6, 15, and 20, and I told you that 20 was in the middle, what would be the next 3 numbers? So it would flip over like that. And those would be my coefficients. This is what is commonly referred to as Pascal's triangle. So Pascal triangle, notice this arrangement of numbers. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. If we continued it, that's where I got the next section. 1, 6, well, and then 15, 20, 15, 6, and 1. So I want you to do the next 2 rows. Okay, so what would my next row look like? I know that it's going to be 1, 7. Then what?
21, 35, 35, 21, 7, 1.
Okay. And what about the next row?
1, 8, 28, 56, 70, 56, 28, 8.
Okay. So remember, these are the coefficients on my expansion. This was the x plus 1 squared, cubed to the 4th to the 5th. So this right here corresponds to x plus y to the power of 6. So I can use the properties that we discovered above with this array to say that if I expand this out, I'm going to get 1 x to the power of 6 Then I'm going to get 6. My x's are going to decrease, so I'm going to get an x to the 5. And my y's are going to increase. So I had no y's here, so I'm going to have 1. Then I will get 15 x 4 y squared. 20 x cubed y cubed. 15 x to the power x squared y to the power 4. Then 6x y to the power 5. And y to the power 6. So my coefficients follow this pattern. My x's go down from 6 to 0. My y's go up from 0 to 6. And in any term, the sum of the exponents is always equal to 6. So with that given, I want you to expand x plus y to the power of 7. So use the triangle, that next row, to write that out. Okay, so if I expand this out, what do I get?
X to the power 7 plus, okay, 7, x to the power 6, y.
Keep going.
Plus 21, x to the power 5, y squared, plus 35, x to the power 4, y cubed. 35, x cubed, y to the power 4, plus 21, x squared, y to the power 5, plus 7x, y to the power 6, plus y to the power 7.
Good.
That's a lot of work.
It's a lot of work, but still a lot easier than having to expand this out 7 times. Okay? So then question C says, which row of Pascal's triangle is equivalent to the coefficients in these terms? So which row is equivalent to the expansion of x plus y to the power of 6? So if I count the rows, 1, 2, 3, 4, 5, 6. This was the 7th row. So x plus y to the power of 7, I will find in which row of Pascal's triangle? The 8th row. What about x plus y to the power of 12?
13,
And what if it's x plus y to the power of n?
n plus 1.
Good. Okay. We're trucking along. The numbers in Pascal's triangle form combinations. So the first row is 0 choices, and I've picked 0 of them. That's how I get 1. There's only one way to pick nothing, nothing. And then 1C1, 1C0, 1C1. And so when I get to the 7th row, I've got 6C0, 6C1, 6C2, 6C3, etc., etc. So if I was in the 8th row, in terms of combinations, what would be my first combination?
7C0.
What would be the next one? And what would be the next one?
7C2.
In terms of numbers, 7C0 would equal 1. 7C1 would equal,
7.
and 7C2 would equal, just flip back to the previous page and look at that row. 21. Okay? In that 8th row, what would the last 3 terms look like?
The exact same, just in reverse order.
in reversed order. So I would have, not the exact same though. It wouldn't be 7C0,
Oh.
it would now be 7C. What would be the very last number?
7C7.
7C7. And then the one before that would be 7C,
6.
and then 7C5.
5.
So the numbers 21, 7, and 1 would be the reverse, but the combinations are not identical. But there still is a relationship with the combinations. 0 and 7 is 7. 1 and 6 is 7. 2 and 5 is 7. So that was that one lesson that we had looked at that said 7C1 was the same as 7C6. Because I take 1, I leave 6 behind. I take 6, I leave 1 behind. It's kind of the same thing. Okay? And then question C says, use Pascal's triangle to write the following as a single combination. So what this looks at is it says this 4C2 and 4C3, when I combine them together, that gives me my 5C3. Because that was the pattern that we saw in Pascal's triangle. I take the two terms, add them, that's how I get the term below. So if I look at 6C0 and 6C1, they're going to combine to give me what? 7C1. So how do I get this first number in my combination? How do I use this to help me get the 5? Add 1 to the 4. So if I have n and n, what would the next one be? When I add these together, I would have n plus 1. How do I get the second number in my combination?
You get the biggest of the less combination.
I pick the bigger r. So 3 and 3, 1 and 1. So what would I have here? R plus 1. Okay. Now investigating three sums equaling 2 to the power of n. So it says complete the table for the sum of the numbers in the first 6 rows of Pascal's triangle. So if I go up to here, these are the first 6 rows. If I add these together, I get 1. 1 plus 1 is? 1 plus 2 plus 1 is? 1 plus 2 plus 1 is? 4. 1 plus 3 plus 3 plus 1 is?
8.
8. And so continue on. So I have 1, 2, 4, and 8 that I've done for you so far. So what did I get in the 5th row?
16.
And in the 5th row?
32.
Okay. All of these numbers can be written as a power of 2. 2 to the power of 0 is equal to 1. 2 to the power of 1 equals 2. So how would I write 4 as a power?
2 squared.
2 squared. What about 8?
2 cubed.
16.
2 to the power of 4.
And 32.
2 to the power of 5.
So if I have n rows, what would that be? 2 to the power of n minus 1. And if I have n plus 1 rows, it would be 2 to the power of
N.
n. Okay. So it says, look at row 5 in Pascal's triangle in combination form. So in combination form, this is what Pascal's fifth row looks like. 4C0, 4C1, 4C2, 4C3, 4C4. As a power of 2, row 5 adds up to 16. Being 2 to the power of 4. So now if I look at row 7, if I add the numbers up in row 7, I would get 2 to the power of what? Where did the 6 come from, Hannah? It's the n. So 2 to the power of 6 is equal to 64. So then if I have a statement, a sum of combinations, NC0, NC1, NC2, NC3, all the way up to NCN, I could say that's going to equal 2 to the power of what? N. So this gives us, or leads into the next statement. Again, we go back to the array, into the expansion. If we look at the sum of the coefficients again, I have 1, 1 plus 1. So this is just taking the Pascal's triangle and putting it into the expansion. It doesn't change. 1, 2, 4, 8, 16. It's still 2 to the power of 0, 2 to the power of 1, 2 squared, 2 cubed, 2 to the power of 4. So if I have x plus y to the power of n, it is going to be equal to 2 to the power of n minus 1. So it'll be 1 less. Oh, wait a minute. Oh, I did this wrong. I started off with the wrong n. Oops. When n is equal to 1, what's the sum of the coefficients? 2. Sorry, I started the wrong part. So everything should be shifted up 1, 2, 4, 8, 16, and 32. There we go. 2 to the power of 1, 2 squared, 2 cubed, 2 to the power of 4, 2 to the power of 5. So this n here refers to the exponent on the expansion. It's not the row number, it's the exponent. So when the exponent is equal to n, the sum of the expansion will be 2 to the power of n. So that's a little bit different than what it said in Pascal's triangle. So then we get the following 3 statements. There we go. Summarize the previous work. So the sum of the numbers in the n plus 1th row of Pascal's triangle is 2 to the power of n. That means in the 7th row, the sum would be 2 to the power of 6. In the 20th row, it would be 2 to the power of 19. Okay? I can write each row out as a sum of combinations. NC0, NC1, all the way up to NCN. When I write this in combination form, the sum is equal to 2 to the power of n. And then the sum of the coefficients in the expansion, x plus y to the power of n, is 2 to the power of n. So when we're talking about the expansions, the n's match up. When we're talking about the rows in Pascal's triangle, it is 1 less. So then we'll look at an example here. It says, determine the sum of the numbers in the 10th row of Pascal's triangle. So what would be the sum of the numbers in the 10th row? 2 to the power of 9. And what is 2 to the power of 9? Okay. If I have the expansion m plus n to the power of 12, what would be the sum of the coefficients in that expansion? Which would equal? Okay. And then part C says determine the value of the following. So I have the sum of combinations. They're all 15s, and I'm going from 0 to 15. So that's looking at the whole row. So that's going to be equal to 2 to the power of what? That would be this second bullet right here. What would that equal? 2 to the power of 15. Which equals?
32,716.
Okay. What's the difference between that one and the second one?
Second one is the 6C6.
So I'm missing the 6C6. Well, that would be the still, instead of having to add all of those up separately, I can look at it as it's going to be 2C6 minus 6C6. By the way, what's 6C6? 1. And what's 2 to the power of 6?
64.
How much?
64.
64 minus 1?
63.
63. Okay, so I'm going to have to figure out which questions I want to give you. So this will be questions 3, 5, 7, and 8. And then next class we'll finish this up. Exploring routes using Pascal's triangle. So I did kind of briefly touch on this the other day. If you look back at the problem that we did the other day with routes with Paul and Catherine, Catherine's method to determine the number of routes from A to B was to go 5 factorial, because there's 5 streets that I have to move, because I'm always moving closer. 3 of those streets were east, 2 were south, so it's that repetition to get 10 routes. And then what Paul had done is he had actually drawn them all out, and he had gotten the 10. We can actually use Pascal's triangle to do this. And the best way to do this is if we take that rectangle and we tilt it on its side. And then we can actually see that triangular array probably a lot easier than we can when it was vertical. So if I look at A to C, there's only one way to get from A to C. There's only one way to get from A to E, because I can't backtrack. So I can't go say, well, to go from A to E, I could go this way. The idea is you're always moving closer to your destination. And then again, if I'm going from A to D, there's only one way. A to G, there's only one way. If I went all the way to the very end, there'd only be one way to get to this point. And right here, if you look, this is the outside arrangement that I get when I put Pascal's triangle into the array. Then I can use that knowledge that we had before where I take the two above, add them together, and that's how I get the one below. So then F would be 2. So how does F compare to C and D? Well, 1 plus 1 equals 2, and that's how I get F. And then H, this point right here, it's the one path and the two paths, so that's how I get 3. So E plus F is what is equal to H. And then I, 1 plus 2, again, I get 3. So taking the number of routes from F and from G. Because what this means is to get to point I can either go through F or through G. So I had 2 paths to lead me to F, 1 path to lead me to G. That's how I get the 3 paths in all. So if I complete the diagram at this point here, I get 3 and 3, give me the 6. 3 and 1 gives me the 4. And together, that's how I get the 10. So that's how I get the 10 routes. Okay? Does that follow so far, Rachel? How did the video go yesterday for you?
I finished the video, but I didn't do the questions because it was like 10:30.
Okay, so now we can go into the next page. So all I've done on the next page is they've taken Pascal's triangle and then superimposed that street setup on it, and then also showed you in terms of the combinations that this works. Because there's one path, this 1 and 0, you're not choosing anything. You don't have any other choices to go. So if we look at class example number 2 and then number 3. Supervisor of the city bus department is determining how many routes there are from bus station to the concert hall. So we want to determine the number of routes possible using Pascal's triangle and using permutations with repetition. So using Pascal's triangle, that's the 1 and 1, 1 and 2, the 1, 1, 1, 1, 2, 1, etc., etc. So I start with 1. That's at the bus station. If I imagine getting to this point here, there's always only going to be one way that I can get to that point, because I always have to be moving closer to the concert hall. Moving down, again, there's only one way I can get to this destination. Hello?
Can you plug these calculators in and charge them? Is that a thing?
Okay. So once I have this 1 and 1 going along the outside, if I just kind of imagine it tilted, I get 1 and 1. So these two corners, 1 and 1, give me 2. 1 and 2, give me 3. 1 and 3 gives me 4. 1 and 4 gives me 5. And I just keep repeating that pattern. 1 and 2 is 3. 3 and 3, 6. 4 and 6, 10. 5 and 10, 15. 1 and 3 is 4, 6 and 4 is 10, 10 and 10 is 20, and 20 and 15 is 35. So I have 35 ways to get from the bus station to this point here. Maybe that point's a bridge or a tunnel or something like that. In order to get to the concert hall, you have to go through that tunnel. So that's where you have to converge. Then from here, these two numbers going along the sides stay at 35. Much in the same way that these stayed at 1. If there's 35 ways to get to this point, there's still only going to be 35 ways to get to this point. The other way that you can look at it is this is 35 and 0. It's 35. 35 and 0 because there's no road up here. Or down here, 0 and 35. 0 and 35. Then I fill this up. 35 and 35 is 70. 70 and 35 is 105. I have 105 down here. and altogether I get 210 routes. So that's using Pascal's triangle. If I used permutations, again, I'm going to take this first rectangle because I have to converge to this point, and I count 1, 2, 3, 4, 5, 6, 7. There's going to be 7 blocks that I take no matter which path. If I go 1, 2, 3, 4, 5, 6, 7, I still get 7 blocks. My repetition is I have 3 blocks that are moving east and 4 blocks that are moving south. So that's to get to that convergent point. And then I have that next rectangular array. How many blocks will I be moving from this point to the concert hall? 4 blocks. And what are my repetitions?
2 and 2.
2 and 2. Now the question is, do I add these 2 amounts or do I multiply them? Why multiply?
Because it's and.
Because it's and. I have to go to here and then to here. I can't do or. Or would be the adding. I have to go to both sections. And this one, 7 factorial divided by 3 factorial, 4 factorial gives me 35. And this 4 factorial divided by 2 factorial gives me 6. Which is the 210 routes that I got. So I could use either system to answer this question. If I look at question 3, it says a taxi company is trying to find the quickest route during rush hour from the train station to the football stadium. Use Pascal's triangle to determine the different routes that must be considered if at each intersection you always have to be moving closer to the football stadium. You can't backtrack. Okay? So again, that's using I start off with my 1 and 1s, going down those 2 initial sides. And then I've got my 1 and 1 is 2, 3, 4, 5. Then I've got 3, 6, 10, 15. Sorry, I'll slow down. Then if I look at the third column, I've got 1 and 3 is 4, 10, 20, 35. What would this point down here be? 15. Because if you think about it, it's like 15 and 0. Which means underneath the 35, what would I have? 50. Okay, and what would I have up in this corner? 4. Because again, think of it as being a 4 and a 0. So then I'd have 14, 34, 69. I'd have 119 routes. Okay. Now, question B says, why can't I use permutations to answer this? Or why can't I go 9 factorial divided by 4 factorial, 5 factorial?
Because it's not actually like a perfect square or rectangle. You
Yeah.
have parts cut out, so it'd be less than what that gives you.
Exactly. It's not a whole rectangle section. So the overlaps or gaps don't allow for permutations. So then those would be your questions for the assignment.